Dear respected viewers, today we are going to have a look at the basics of SMPS. Before we can understand the basics of a SMPS circuit, we will have a look at the traditional power supplies first. Now, what are the basic main components of a regulated power supply? In the initial stages, we will require a step down transformer. Well, as you can see from the figure here, a step down transformer will have two coils. One is the input side, which is called the primary, and the other one is the secondary. So if the number of turns in the primary is greater than the number of turns in the secondary, it usually is termed as step down transformer. So before you can choose a step down transformer, you will need to know what are the requirements of your circuit and what are the load requirements. So whenever you go to a market trying to buy a transformer, there they will be asking you two things: what is the voltage and what is the current ratings. There is another thing that they may ask you is whether the transformer is bridge type or center tap type. So the requirement of the load defines the current that needs to be pulled in the secondary part of the transformer. So you will have to select the transformer in that manner. The next part is the power diodes. When we are talking about power diodes, these are general purpose power diodes and generally used in all the circuits. And the example is 1N4007. So this is the physical picture of a diode where you can see we have two terminals and a black plastic package where we have a silver mark on it. Now this silver mark indicates that the terminal associated or very near to it is the cathode or the N type of the diode, and the other part is the anode or the P type section of the diode. The third part, which is the very important one, is the regulator part. Now, suppose you want to make a regulated power supply whose output voltage will be fixed at a positive DC 5 volts, then you can use readily available voltage regulators like this. Here we can see it is a 7805. It is a fixed positive voltage regulator, and 7805, yes, 05 means it will, the output voltage will be regulated at plus 5. It is a three terminal device, and it's a three terminal device where one is the input. Usually the range is dropout voltage plus the maximum, which is somewhere around 30 volts DC at the input, and the output will be fixed at plus 5, and this is the reference terminal. So this is the a block diagrammatic representation of the internal parts of a regulator, where we can see it is having a pass transistor which allows the current from the main to be passed on to the load circuit or the output circuit. Then we have a referencing, then we have feedback where the error voltage is checked and the other necessary adjustments are done so that the output voltage remains the same. Well, now together if we see the traditional regulated power supply, here we can see we have a transformer where the high AC voltage is stepped down and we get a low AC supply. It is then rectified. Now when we step down the transformer voltage, you have to remember one thing: the input is also AC as well as the output. So here you are stepping down the voltage, nothing else, but the energy remains constant. That means the power inside here and the power inside here remains the constant. And then we have the rectifier section. This rectifier section can be constructed out of in the bridge configuration with the four diodes, or you can have full wave rectification with two diodes. For that, you may require a center type transformer. Then after rectification, what you will get is a rectified output with all the pulses on the positive side. We usually call this pulsating DC. Now, this particular waveform here we can see is not typically a DC voltage, though we have the waveforms on the same side, that is on the positive side, but still there should not be any frequency in a DC voltage. So we have to filter this out. So in order to filter this, we have to have capacitors, and when we apply capacitors, the capacitor will smoothen out the pulses and we will get a DC at the output. So we'll get a filtered DC at the output. But we have to remember one thing: this particular section till the filtering is the unregulated part. Unregulated part here means if the input voltage falls, the output voltage of the transformer also falls, and the other parts like rectifier as well as the filter here also, the impact will be the same. So uh, again, if there is a load which is trying to extract more load current, it can also reduce the output voltage. So there is no mechanism to regulate the output voltage. So what we do is we try to get three terminal regulators or other regulators which are available in the market to regulate the output voltage to a certain fixed voltage, irrespective of the load current drawn from the system. But one thing we have to remember here is this particular type of regulated power supply typically suffers from a huge drawback. The drawback is when we design this particular type of regulated power supply, we assume that the input voltage is not fluctuating a lot. So the dropout voltage, that is the voltage which is dropped out uh, across the regulator, plus the input voltage and the output voltage should be less than the dropout plus the input voltage. Here again, we have to see the dropout voltage is the inherent property of the regulator. So what we can do is we can actually choose a higher rating at the input, so that even if the voltage falls at the input of the transformer, it will not affect the regulator. But the line regulation of this is not that good. When the input fails, if the voltage falls considerably, the the regulator fails to regulate the output at a fixed voltage. This is because we are trying to regulate the voltage on the secondary side of the transformer. So the secondary side of the transformer's voltage is dependent on the input voltage. So if the input line voltage falls, the output also falls, and it will directly affect the performance of the regulators. So the main disadvantage of this type of a circuit is of the secondary regulation. Now this is a practical circuit that we can see here. This is the step down transformer, and this is the bridge rectifier using four diodes. Here we are using a 1N4007. It is capable of handling the line frequency. Usually, our line frequency in the Asia part of the continents or the country, in our country, it is 220 volts and 50 hertz. And this diode is well capable of handling the line frequency, which is the 50 hertz. And then after the rectification, we get a pulsating DC at the output, which is again which is again filtered by the capacitor. Usually in the practical circuits we use 1000 microfarad 63 volts. Now the voltage again depends on the output voltage that you are expecting. So if the output voltage is say 12 or 18 or within 20 volts, then it is very safe to use a voltage 35 volts or more. Voltage which is almost equal to the expected voltage here is not recommended. It is always recommended to have a capacitor voltage larger than the expected voltage across the capacitor. Now, after that, we have a three terminal regulator. As it's seen here, the input is connected to the number one pin of this 7805, which is a three terminal 5-volt regulator. And we have certain ripple capacitors to filter out the ripples connected across the input and the ground, and also the output and the ground. The output is achieved from the third terminal, and the second terminal of the regulator is grounded. So whenever you switch on this power supply, you will get a fixed output voltage. And usually this type of regulators can provide a constant voltage for approximately 1 amperes of current. Now provided, now you are saying 1 ampere at the output. Now your transformer should be capable of delivering 1 ampere or more than that. So these are the design specifications we usually take while designing a power supply. But again, this traditional power supply is providing a secondary regulation. That is, we are providing the regulation on the secondary side of the transformer, so it will suffer from um, from a regulation when the input voltage fails. When the input voltage fails, the secondary side of the voltage also fails, and it will directly impact the regulator. Now, we will outline the disadvantages of traditional power supplies. It is having a very poor efficiency. It is between 30 to 60%. It it usually generates a lot of heat. So heat sinks are required to cool down the regulators used in the circuit. Then we have regulation is usually achieved. We have already discussed that it is achieved in the secondary side of the transformer only, and it fails to regulate the output voltage if the input voltage of the transformer falls to a greater extent. So, to overcome this sort of problems, we usually try to make better power supplies. Now, the switch mode power supplies are have proven better in many applications. So, to understand the switch mode power supply, we will understand only the basics of it with the help of few block diagrams, and only will be trying to understand the forward converter type of SMPS. Now let's see what SMPS is actually. It is a switch mode power supply. It's an electronic power supply that incorporates a switching regulator to convert the electrical power efficiently. So here in this particular circuit, we'll have a high speed switching transistors trying to regulate the output voltage. Again, The main difference between the traditional power supply and the switch mode power supply is here the regulation is provided in the primary side of the transformer. So when the regulation is provided in the primary side of the transformer, the secondary automatically gets regulated. So if you do not require a very high precision regulation on the secondary side, actually in most of the circuits, in SMPS circuits, the secondary side just is having rectifiers and filter circuits which directly provides the voltage to the required sections. Now, here we can see the primary regulation is done to achieve increased efficiency. Then obviously what we have just discussed, that the high speed switching transistor, the MOSFETs, are used to boost the frequency of the switching, and we will use the pulse width modulators to control the switching action. Now let's move on to the very basics of the SMPS circuit. And to start with, we have a, a, a basic block diagram of an SMPS. Here we can see we have a initial section, which is the rectifier section. Then we have the switching section with the chopper transformer or the high frequency transformer. Then the secondary part is rectified, filtered, and a feedback is provided from the output to the control circuit, which actually tries to regulate the output voltage depending on the load that is connected at the output of the SMPS. Now, let us try and understand each and every section. Uh, Here at the input, we can see there is a filter. Now, why do we need a filter? The filter, usually we call it as chokes, and these are used in the input side of the SMPS. Now we have to remember one thing, that the line frequency of 50 hertz gets boosted to around the 20 kilohertz or more than that. So a circuit having high frequency at the heart of it may create some noise in the main line. So in order to avoid that, because in the main lines you may have different type of equipments connected, so if there is electromagnetic interference or high frequency noise interference into the system, then the other devices may get damaged. They may create noise. So in order to do that, one of the input side on the input side, to prevent high frequency noise from reaching the input sources, we usually go for a filter. Now a filter, an inductor filter, it usually looks like this. Now let's move on to the next part, that is the rectifier section. Now the rectifier section is preceded by two portions. One is the switch, a physical switch which can be used to switch on the circuit and to turn off the circuit. Then we have a fuse. Now this fuse is very important. So whenever anything goes wrong inside the rectifier section, this fuse will blow off to protect the other sections of the power supply. So whenever you find the fuse at the input blown, you need to check the rectifier circuit and the diodes and the filter sections to check for short circuits. Now, when we are talking about the input AC rectification, here we can have normal power diodes that are 1N4007 can be used. Even greater amperage diodes can also be used, but normal power diodes are used in this section because we are only trying to rectify the input AC voltage, which is having a line frequency of 50 to 60 hertz. So 50 to 60 hertz is can be handled by this normal power diodes. But remember one thing, at the output When we have a rectifier circuit at the output, these diodes cannot be used here at the output, since the output will have a frequency much higher compared to the line input frequency, which is 50 hertz. Here the output frequency may be more than 20 kilohertz. So you need to have rectifier diodes, power rectifier diodes, which can handle such frequency. So if you connect a diode of this category at the output, it will immediately blow off. Now, uh, a typical bridge rectifier circuit looks like this, where you have AC inputs usually provided to the dissimilar junctions of the diode. You can see here we have N, we have a P, and this dissimilar junction will have one AC input, and the other will again have the other AC input. Now, the output is usually available on the similar junctions, that is, from the P sections, you will get a negative voltage, and from the both N types, you will get a positive voltage. So, this particular section is usually built here, and then we will have the filter circuit. Now, as you all know, when a particular thing is rectified, we'll get a pulsating DC at the output. Now, we have to remember one thing here: we are directly rectifying the line voltage, which is 220 volts, and this 220 volts is the RMS voltage. So, if we convert that into peak, we will get a voltage approximately equal to 311 volts. So when we rectify, the peak of the voltage will be 311, and that will be available across this filter capacitor. Now the filter capacitor here ranges from 47 microfarad to 100 microfarad in case of SMPS, and the voltage of the capacitor has to be greater than 400. Some in some circuits you will see it is around 400, or in 450 it has to be greater, because when we rectify the line voltage, the peak will appear across the capacitor, which is here. This is the peak after, this is the line input, and this is the peak after rectification. So when the capacitor charges and holds it, the peak will be around 311. So the capacitor should be able to handle such voltage. So it is always safe to have a voltage around 400 or more than that. So this is the filter part of it. Now let's move on to the next part, where we will see that one end of the rectifier gets directly connected to the high frequency transformer or the chopper transformer of this SMPS. Now it looks similar to this. As you can see, we have a AC commercial line rectified by diode in bridge configuration, filtered, smoothened out by filter capacitor, and one end of it gets connected to the high frequency transformer. Now, now you can see that the DC, which is filtered through a capacitor, is connected to a transformer, and we all know a transformer cannot work on DC. So in order to induce current to the secondary, you need to somehow change the current through this, so that a voltage will be induced in the secondary side. So in order to do that, what we do is we go for a switching action, which is usually carried out. This is just a diagrammatic representation where we are seeing a physical switch. Now this particular switch is getting controlled. The switching action is getting controlled. The switch will switch on, the switch will switch off. It will create a current to pass through this, and it will induce a current on the secondary side. So in order to do the switching part of it, will require a power transistor, power switching transistors. It should be power switching transistors, which will be able to handle the current that needs to be carried through it, and also it should be capable of switching at higher speeds. So we can have IGBT, that is insulated gate bipolar junction transistors, or we can have insulated gate field effect transistors. We can have MOSFET, power MOSFETs to in order to achieve this particular action. So now let's move on to the next part, where we'll be discussing the SMPS, which works on forward converter type, which is a forward converter type. Now let's see how it works. Now, in a forward converter type of an SMPS, we can see the input section is connected to a DC. One side of the transformer is connected to the DC. The dot signifies that this part will start conducting, this section will start conducting, as well as the other part as well. In this case, we can see the DC is connected to one end of the transformer. The other end of the transformer is usually connected to the drain of the power MOSFET. The source is connected back, and the gate is connected to a high frequency oscillator. Now, the oscillator will actually provide a on period and a off period. Now we have to remember one thing: this time period of oscillation, which is a on period and a off period, remains the same. It remains a constant, and depending on the design specification, design needs, it may be more than 15 kilohertz, and in some SMPSs, in the televisions, which were earlier televisions, used to have 15625 kilohertz, so that it matches the frequency of the horizontal scanning. And uh, and uh, uh, and in order to achieve that, they used to design the SMPS, which were used to switch at 15625 15625 hertz, which is 15.625 kilohertz. Now it all depends on the design and where it is to be used. Depending on that, uh, the frequency is determined. But we have to remember one thing: once the frequency is determined, this remains the same. So if time period of oscillation remains constant, the frequency of oscillation remains constant. So only thing that may change is the duty cycle of it. I don't know what is duty cycle. Duty cycle is the time for which it will remain on and time for which it will remain off. So that will again depend on the feedback circuit. Now, before we can understand that, let us first try to understand what is forward converter. So in forward converter, when the transistor or the MOSFET is switched on using a high pulse, the primary coil of the transformer starts conducting. So a current will flow from the primary coil, from the DC regulated part, unregulated part, to through the transformer, through the MOSFET. This will actually induce a voltage on the secondary side of the coil. Now, the in the secondary side of the coil, the induced voltage will be same as that of the primary. So in this case, we can see that if the induced voltage is same as that of the primary, then this side is positive with respect to the other side of the secondary side of the transformer. Then this particular diode will get forward biased. Now, when this particular diode gets forward biased, the current will flow through the inductor and to the load, also charging the capacitor. Now, this capacitor usually is the filter capacitor, but it will also act as a storage device, which will provide a significant amount of storage when the transistor is off. We will discuss that in the next slide. Now in this slide, what we can see is the voltage induced in the secondary side is the same as that of the primary. So because of that, the diode D1 gets forward biased, and during this period, both the inductor and the capacitor store energy in the form of magnetic as well as electric field respectively. let's see what happens when it is off. Now, when there is a low pulse, the transistor or the MOSFET is off, hence the primary coil stops conducting. This will also stop a induced voltage current into the secondary side. This sudden change or a drop in the current will generate a back EMF. Because of the back EMF, what happens? Thus, the polarity across the inductor changes. Now here this becomes plus, this becomes minus. just because of that just because of that, the diode D2 now starts conducting, and as the energy in the inductor is almost finished, this capacitor which had stored the energy in the previous cycle now will try to discharge through the load, and it will work temporarily as a source to the load. So when it is off, when the transistor is off, the stored energy in the inductor as well as capacitor now acts as a source for the load till the transistor, this switching transistor again switches back on. So this is how a forward converter type of a SMPS actually works, and we get a regulation. Since we are switching the primary side and try to achieve a regulation here, we do not require any specific voltage regulators on the secondary side. So this is how a forward converter type of a SMPS works. Now let's sum up the entire thing. Just by looking into this block diagram. Now again, let's see what happened actually. The input line gets rectified, filtered by the capacitor, rectified by the um, diodes, power diodes, and then after smoothing it out, it is applied to a circuit where we have a transformer directly connected to a switching transistor, and it is actually in the second in the primary side, and the switching action is actually carried out by a oscillator, and we have a PWM or a control circuit which gets the information from the secondary side of the transformer. Now, in the secondary side of the transformer, you will have a load connected across it. So the load will try to get current from the system or the secondary power section of the transformer in order to maintain its functionality. So during that, load current will flow from here into the load, and because of that, there may be the output voltage may reduce if the load current increases through the load. So when that happens, what will happen is there is a feedback path which will actually sense the error that is being generated, and that particular error can be rectified by this control circuit by switching the transistors. The speed of the transistor, the switching speed of the transistor will be increased in order to compensate that, and vice versa. And here we can see the feedback is usually provided by an opto isolators or opto couplers. The the transformer also acts as an isolator because the primary side is completely isolated from the secondary side. So 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 in order to get a feedback from the output to the control circuit, we can use optocouplers or opto isolators, where we have LEDs and photo sensors. The Depending on the current, the LED brightness, the intensity of LED will increase or decrease, and correspondingly it will create a difference voltage at the output of the photoconductors or the photosensors, which will again create a reference change in the control circuit, and this control circuit is equipped with error detection, which will either increase the switching speed of the transistor, keeping the time period of oscillation constant, or reduce the switching speed, again keeping the time period of oscillation constant. You have to remember that this will only change the duty cycle of the time period of oscillation. So this is how a simple this is the simplest example, simplest explanation of SMPS. I hope the explanation will give you a brief insight about a simple SMPS circuit. Now, to conclude, we had a very brief explanation of regarding the disadvantages of the regulated power supply, the traditional regulated power supplies. Then we have seen certain advantages of SMPS. Then we went on to see the basic construction of SMPS. We had restricted our discussion to forward converter type SMPS, and we also had a very limited discussion on feedback using optical couplers or optical isolators. Then we have a very brief discussion on PWM. Again, we had uh, isolation created using the high frequency transformers, and and a very block diagrammatic representation of a SMPS, and a basic understanding of it. So thank you very much for watching this video. Thank you again.